Let's take a look and review our gas laws. So this is Boyle's law, Charles's law, Gay-Lussac's law, and Avogadro's law. This is something that should have been covered extensively in your prep class, so this all should be a review. All right, let's take a look. So Boyle's law. So Boyle's law is going to relate pressure and volume. So Boyle's law tells us that pressure and volume are inversely related. So when I look at this data table here, I've got some pressure, I've got some volume. Now, if I graph volume versus pressure, I get this curved line as shown in picture D. In order to get a linear relationship, I have to do something like do 1 over pressure in order to get it to be linearized. This is because it's that inverse relationship. When one goes up, the other one goes down. So we know from Boyle's law that we have P1 V1 equals P2 V2. Okay? When I think about gases, on a molecular level, on a particulate level, if I do something like I, increase the pressure, I'm going to decrease the volume. Okay? When I think about things like scuba diving, all right, at sea level, at a depth of 0, we have a pressure of 1 atmosphere. If I'm all the way down, I'm at a pressure of about 3 atmospheres, okay, at a depth of 20 meters. Now, a scuba tank, you've got your pressurized oxygen, you can breathe, you're good to go, okay? So as we go down, we're getting a higher pressure. More water above you, more pressure pushing on you. So, when we breathe, does anybody who's watching this know how we breathe? And this is actually an interesting topic. You may or may not have seen some stuff on this during COVID when there was talk of potentially bringing iron lungs back. So our modern day ventilators are a positive pressure system. They force air into your lungs, and that allows people that aren't breathing to breathe. Now, the way the iron lung works, though, is it actually is less stress on your body because it does it in a way that is more natural to the way you breathe. So when we breathe in, what we're doing is we are reducing pressure in our lungs, and so air is able to flow into that vacuum. So we're not forcing air in, we're reducing pressure and air flows in. When we breathe out, we are increasing pressure and we're pushing that air back out. And so in an iron lung, it works by letting the chest expand and contract more naturally. A modern ventilator that, goes in, it is going to do a positive pressure. It's going to force air into your lungs. Okay, so given that information, let's say instead of a scuba tank, we have a really long snorkel. Can you breathe at 20 meters depth with a pressure of 3 atmospheres with that snorkel? No, you cannot. So at depth, what's happening is you can't reduce the pressure in your lungs because now you've got this external pressure pushing on you. And so you're unable to reduce the pressure in your lungs. And so that snorkel tube that's all the way at the top, you're not going to get any air to rush into your lungs because you cannot reduce the pressure and allow the air to flow into your lungs. So you got to use scuba tank, cannot use a long snorkel. All right, our next law is Charles's law, okay? When I'm looking at Charles's law, I'm relating volume and temperature. This one is directly proportional. When one goes up, the other one goes up. When one goes down, the other one goes down. And so you can look at this with a balloon. If I blow a balloon up at room temperature, and then I put the balloon on ice, my balloon is going to shrink down. My temperature cools down, my volume goes down. Okay, so volume and temperature, directly proportional. Volume 1 over temperature 1 is equal to volume 2 over temperature 2. Okay, all right. So, one way we can cool it down is by using liquid nitrogen. This is really fun to do. I used to get, when I was a grad student and I was at a major university and we had liquid nitrogen available in the ice room. Most major universities in their chemistry lab facilities will have an ice room, and the ice room is where you go to get regular ice. They stock dry ice, they stock liquid nitrogen, and so it's there for all of the labs. And so when we would have our chemistry club and we'd do outreach, we would sometimes get a bunch of liquid nitrogen and we would do this demo at our events. And so it's a lot of fun to, dunk the balloon in liquid nitrogen, have it shrink, and then bring it out and have it expand, and then dunk it and have it shrink. And it works for a while. Eventually all the expanding and contracting wears out the rubber of the balloon and eventually it gets a hole in it. But it's a fun demo to do. Okay. All right, and because they're directly proportional, when you plot volume versus temperature, it's already a linear relationship. Okay, then there's Gay-Lussac's law. This one's relating pressure and temperature. It is also a linear direct proportional relationship, and so one goes up, the other one goes up, and vice versa. So here I have a picture. I have a tank at 300 Kelvin, and the internal pressure is 1 atmosphere. I double the internal temperature to 600, and now my internal temperature, or internal pressure, is 2 atmospheres. And so we get our P1 over T1 equals P2 over T2. Okay? All right, and then we get Avogadro's law, and this one is relating volume in moles, also directly proportional. So here I have 1 mole of a gas, here I have 2 moles of a gas, and so I increase the number of moles, and that pressure went up too. Okay? Or volume, I mean. All right, so here we have our summary. So when we solve problems with these gas laws, what we're going to do is first we have to identify condition 1, and then we identify condition 2. And we figure out what variable is missing, and then we solve. Okay? All right, so here I have some helium. I'm filling balloons. Each balloon has a certain volume and a certain pressure. Okay? So I want to know, given that my tank has a volume of 2.3 liters and a pressure of 12,800 kilopascals, how many balloons I can fill if my balloons have a volume of 1.5 liters and a pressure of 1.25 atmospheres. Okay, so what I want to know is I'm going to need to figure out the total volume of helium that I have available to me. And then once I know the total volume, I can figure out, with knowing that each balloon has a volume of 1.5 liters at a pressure of 1.25 atmospheres, how many balloons can I fill? Okay? Now, in this problem, our temperature is constant, so we don't need to worry about temperature. So the only 2 variables that I need to be concerned with are pressure and temperature. So this is going to be a P1, or not pressure and temperature. Temperature is constant. Pressure and volume. This is going to be a P1 V1 equals P2 V2. Okay? All right. So let's take a look. We have P1 is 12,800 kilopascals. Let's put that into atmospheres. So 1 atmosphere for every 101.325 kilopascals. And so we're going to get 126 atmospheres. Okay. And then my V1 is 2.30 liters. My P2 is 1.25 atmospheres, because that's what we're filling each balloon to. And my V2, we don't know. Okay, so let's figure out what that V2 is so that we know exactly how much volume of gas we have to fill our balloons. Okay, so our V2, when we rearrange, we're going to get P1 V1 over P2. So 126 atmospheres, 2.3 liters, and then over 1.25 atmospheres. We're going to get 231.84 liters. All right, so that 2.3 liters of gas I have sitting at 126 atmospheres. If I were to lower the pressure to 125 atmospheres, now that lower pressure gives me a higher volume. And so I'm going to expand my gas out to 231.84 liters. We're going to round this to 232 liters. So at the lower pressure, I have 232 liters of gas available to me. Okay, our problem told us it takes 1.5 liters to fill each balloon to that pressure of 1.25 atmospheres. So we're going to do 232 liters. I have one balloon for each 1.5 liters. So I'm going to get 154.56. Okay, we're filling balloons. So how do you think we're going to round this? I'm not figuring out how many half balloons I can fill, right? I have to figure out how many total balloons I can fill. 154.56, well, that 0.56 doesn't really round up to another full balloon. So what I can fill is I can fill 154 balloons. Okay, so that's how many balloons I can fill with that particular helium tank. All right, now helium-filled balloons are also used for atmospheric research. So we've got a balloon that we're going to launch at a temperature of 22.5 degrees Celsius. At that temperature and where they're at, the pressure is 754 millimeters of mercury, and we've got a volume. Now, we want to make sure that when the balloon rises, that we're not going to pop the balloon. So we need to know what the new pressure at the new height is and what the temperature is. Oh, this cut this off. Dang it, I thought I fixed all these. This is, the new temperature is negative 33 degrees Celsius. Okay? All right. So now we have a pressure, a temperature, and a volume we have to contend with. All right, so when I read through the problem, P1 is 754 torr. V1 is 4.19 times 10 to the third liters. And then T1 is 22.5 degrees Celsius. Okay, think back to prep chem. When we're dealing with temperature in any of our gas law problems, what units does the pressure have to be in? Has to be in Kelvin. So this is going to end up being 295.65 Kelvin. Okay. P2 is 70 torr. So at the new altitude. V2, we don't know what the volume is going to be, and that's what we need to know to make sure that the balloon we send up is not going to pop. Okay. And then T2 at the new altitude was negative 33 degrees, which is 240.15 Kelvin. Okay. So I have P1 V1 over T1 equals P2 V2 over T2. I need to solve for V2. V2 is going to be P1 V1 T2 over P2 T1. Okay, we have our variables defined. We're in appropriate units. The pressure units match. Temperatures in Kelvin. We can go ahead and solve. Okay, so we're going to get 754 torr, 4.19 times 10 to the third liters, 240.15 Kelvin over 70 torr and 295.65. And we're going to get 3.66 times 10 to the fourth liters. So we have to make sure that our balloon is rated to contain that volume of air. All right, so those are our individual gas laws.